All right, this module covers lateral directional dynamic stability. We'll start with the big picture. There's 5 classic modes of motion. And so far in previous lectures, you learned about the longitudinal modes, which really were derived from a 4th order polynomial that was factored into 2 second order systems. And the first was the short period mode, and then the second one was the phugoid or long period mode. Well, this time we're going to break the lateral directional modes down, and we'll again get a 4th order polynomial that we'll need to factor, only this time it'll factor into 2 real factors and then 1 complex pair. And so we'll get a roll mode, which is 1st order, a spiral mode, which is 1st order, and then a Dutch roll mode, which is a 2nd order mode. And you can see in terms of root locations on the S-plane where those modes fall. We'll now break down each of the 3 lateral directional modes one by one, and we'll start with the lateral axis. Pure rolling motion is the simplest case of lateral aircraft motion. We can assume that the aircraft is free to roll about its x-body axis, and again under a constant speed, straight line horizontal motion. We can model this in the wind tunnel where we can have a bearing that we attach the airplane to and really only exercise the aileron inputs so that the airplane rolls about this x-body axis. But based on that, we can get really good analysis on what the roll mode is in the wind tunnel. When you do an analysis of, say, pure rolling motion, it's always good to start with an equation. And for this, we're going to start with a non-dimensional equation of motion for rolling. It's linearized for disturbance about the steady condition. So we see that roll rate is p, and so we have roll acceleration, and it's a function of all the variables on the right-hand side. But in general, we're going to constrict it to just pure rolling motion. So we'll see that yaw acceleration and side slip and yaw rate and even delta rudder, we're going to make all those 0 so that we only have the aileron input and we only get rolling motion. So with those as simplifying assumptions, we get down to a 1st order differential equation. So that's nice and simplified. So we have delta p dot equals LP times delta p plus L delta A times delta A. So this equation right here. And so the idea here is you would want to bring the delta p term to the other side. Then you would have the homogeneous equation on the left-hand side, and then you would have the forcing function or input on the right-hand side. So let's do that. At the same time, I went ahead and substituted in for LP and L delta A to use the non-dimensional ones. So there's LP is comprised there with its different parameters, and then L delta A is what we have left over multiplying our aileron input. When you do this, then we basically can see the dependence on our roll damping stability derivative CLP. So when we're looking for free motion characteristics, we only have to look at the homogeneous equation, so we can ignore the right-hand side for now. And we see it simplifies when we go over to Laplace to S minus LP equals 0. So we can solve for S to get our characteristic roots, in this case 1, and there it is. And we're going to basically define the time constant to be -1 over that. And if you remember time constants, when we look at the free response back in the time domain, the time constant is going to be right here in our exponential term. So the time constant for pure rolling motion is going to depend on our roll damping parameter CLP. So that's the dependence right there. We know that typically CLP is negative, and that's going to result in a positive time constant. So from this analysis, we know that the free pure rolling response is going to be non-oscillatory, and it's going to decay. It's going to be stable. Here's the time-based solution for a step input in aileron. And this is what it looks like on a graph. So we see that the roll rate will grow over time, but eventually it will level off, and that level off point is going to be our steady state roll rate value. So it'll asymptotically approach that. And what we can do once we have a plot like this is, once we know the steady state value of roll rate, and there's an equation for that based on the equation above, but once we know that value, we can multiply it by 0.63, and that by definition gives us our time constant. Let's go through an example with a real aircraft, so the F-104. So it's flying at sea level with a speed of 87 meters per second, and we have the following roll characteristics with LP and L delta A given. So we want to determine the time constant for the roll motion and its pure roll response to a 5-degree step change in the aileron deflection. So we know that the roll mode time constant is just given by that formula, which is going to be 0.77 seconds. And we know that our roll response to the step input, once we start substituting the variable values of this and this, go into these two. And then we want to put our 5-degree step in here, but obviously change the units to radians. But when we take these constants and that 5-degree step once transferred into radians, it's going to result into an overall number of 0.31. And then we take the tau value from here and we put it right there. And that gives us our time response. Again, a lot of things were given in meters and seconds and radians, but I don't think well in radians. So it's always good to, once you have the response, you can always change back to degrees per second. So that's what we did here. You can see the steady state roll rate for the F-104 is 17.8 degrees per second. Again, our 5-degree aileron step input, and we see how it builds. As an engineer, we want to get an idea of how we may want to change the roll response. We may want a longer time constant or a shorter time constant. So we can look on the S-plane and see that for our first order mode here, the roll mode, if that pole moves closer to the origin, things will slow down. If it moves farther away from the origin or farther left, you'll get a quicker response or a shorter time constant. One thing to note that it's a linear system, so we have a step input in aileron, and let's say that gives us the response here, the first one. I can also put a step input that's larger in magnitude, and it will give me, yes, it will give me a higher steady state roll rate, but it won't change my time constant. It is a linear system, so the time constant tau r will be the same whether the step input was small or whether it was large. The time constant doesn't change. The only thing that does change is the steady state roll rate that's achieved. Now we'll move on to the second lateral directional mode, and that's our spiral mode or yawing motion. So pure yawing motion is the simplest case of directional motion. We can assume the aircraft is free to yaw about its center of gravity. In a wind tunnel, if we make our axis of rotation in the wind tunnel right there, and so that means that really a change in the wind tunnel anyway, a change in heading is directly mapped to a change in side slip, but note they differ in sign. Heading changed to the right-hand rule. Side slip beta is a function of wind in the right ear is defined to be positive. But in general, the displacement of the angle itself are matched, just the sign is you have to account for. And we have yaw rate is now psi dot or minus delta beta dot, and then yaw acceleration, etc. But in the wind tunnel, we can do our analysis about pure yawing motion. Again, we'll start with the basic equation for yaw acceleration, non-dimensional equations of motion, linearized. And we're not going to put any aileron or rolling motion in, so we'll be able to knock those terms out to zero. And then I also showed that we also can always relate yaw acceleration to our side slip information. So yaw rate is beta dot, yaw acceleration is beta double dot, with the negative sign included. So making those simplifications, we get down to a second order ordinary differential equation for pure yawing motion, shown here. And so again, the idea would be to bring these types of parameters on the left-hand side, keep this on the right-hand side as the forcing function, and then we'll substitute in the various non-dimensional stability derivatives. So there's our NR, our N beta, and our N delta R on the right-hand side. Again, we do this so we can isolate the effects of our aerodynamic yaw damping, CNR. Once again, our free motion characteristics can be studied just using the homogeneous equation. So we'll set the right-hand side to 0. That gives us a second order characteristic equation. So we're going to have a damping ratio and a natural frequency. We can do the math there and figure out that the natural frequency is the square root of N beta, and then substituting in the non-dimensional terms, we see our Cn beta affects natural frequency. And then for the damping ratio, we also get NR, and so we're going to see our CNR term as well as Cn beta impact those. So frequency depends on directional static stability, Cn beta, but the damping ratio depends on both directional static stability and aerodynamic yaw damping. We see here that the free response in time is going to be sinusoidal with multiplied by an exponential term here, that as long as everything's stable, that will decay over time, but it's a sinusoid, and we see that the damping effect. Here's different plots for different damping ratios, 0.2, 0.3, etc. Here's higher damping ratios, so less overshoots, 0.7 all the way out to 2. Let's walk through another aircraft example. In this case, we're given N beta, NR, and N delta R, and our job is to determine the damping ratio and the damped natural frequency of the motion, and then describe the free yaw response. So our homogeneous equation given those parameters is shown here. There's the characteristic equation in terms of S, quadratic. We can easily solve that, and it'll turn out that the natural frequency is 2.13 radians per second. Damping ratio is 0.178. Once I know natural frequency and damping ratio, I can substitute those in here and get our damped frequency. In this case, it's 2.096 radians per second. So we know that the free response is decaying, which is stable, that's good, but it's oscillatory motion with a damped frequency of 2.096 radians per second. Now we know that the lateral directional equations are coupled, and so we really got to solve these using our matrix form of modeling, the x dot equals ax plus bu, given the linearized equations of motion up top. Right, all these equations here, we can put it in the state-based model. If we have a state vector as defined as delta beta, delta p, delta r, and delta phi, the transpose of that vector, so that's going to be our state vector. And then, unlike the longitudinal axis, we do have two inputs, right? We have aileron and rudder. So our u, our input vector, to this system of equations is consisted of two things, the aileron and the rudder. So in the model, based on the previous equations of motion and the state vector and input vectors defined, we can then determine what the A matrix and the B matrix are. And here's the values of the A matrix. Notice there's a parameter H that occurs frequently, and so sometimes, just to ease up the notation, you can define that off to the side and just call it H. And then for our input matrix, Same thing here. We've got 2 columns and 4 rows as it should be for our 2 inputs, and we again have the H parameter embedded and defined here. So that's the A and B matrices for this system. With the A matrix defined, which is the plant of the system, which is going to help determine our modes of motion and our characteristics, we'll use that A matrix and solve the determinant of SI minus A, set that equal to 0 on the right hand side, and that's going to give us, at least in the denominator of any transfer function, a 4th order polynomial, like we saw a 4th order polynomial when we solved the longitudinal equations. So we'll again get one for the lateral directional, only this time it will be factored into 2 real and 1 complex pair. The first real solution or real factor or root will be the roll mode or rolling motion. The second one will be spiral motion or the spiral mode, and then the complex pair has the name Dutch roll mode. And we'll get more into those as we go on through the slides. In our top level analysis of these modes, we'll see that the roll mode, it's a first order mode, it's going to result in rapid changes in bank angle, and it's really going to determine or give us an idea of how quickly an airplane can achieve a steady state roll rate, but it's stable, always highly convergent. The second first order mode, the spiral mode, results in slow changes in bank angle and can be either slowly convergent or actually unstable and divergent. And it's often unstable in many aircraft. The third mode, the Dutch roll mode, the second order one, results in rapid changes in side slip and bank angle, and is typically lightly damped and low frequency. To illustrate how these modes of motion occur, we'll use an aircraft example of a Boeing 747, large mass of 288,000 kilograms, steady flight, 40,000 feet, Mach 0.8. And for this condition, this is the A matrix for the Boeing 747. Once we have the A matrix, we'll set up our determinant of SI minus A, set it equal to 0, and that will give us a 4th order polynomial with the various coefficients for B1, B2, and B3 shown there, and we'll be able to factor that into 2 real factors and a complex pair. And for this case, the roll mode is the S plus 0.56. So there's our roll mode factor. And we can solve for our time constant, our roll mode time constant. In this case, for the Boeing 747, it's 1.7754 seconds. The next first order mode is our spiral mode. Again, we know what the pole location is. The time constant is given by that equation there. And so that you can see here for the spiral mode, the time constant is quite large, 137.72 seconds. The complex pair here is our Dutch roll mode, which has factored into a complex pair with of imaginary solution here with a real part and imaginary part. But based on that, we can get the damped frequency of 0.948 radians per second and a damping ratio, again lightly damped, of 0.035. So first order modes give us time constants, second order mode gives us a frequency and a damping ratio. When plotting the poles or eigenvalues on the S-plane, we can see that the spiral mode is going to be, again, on the real axis, very close to the origin. Could be on the left or right half plane because it can be unstable. The roll mode is going to be another first order, so on the real axis, but it's going to be well left on the left half plane, so always stable, always convergent. And then our Dutch roll will be a complex pair of poles with an associated damping ratio and natural frequency. So now we'll walk through each of the three modes in a little more detail with some pictures, with some time histories, and talk about different requirements from the FAA or the military, and then from an engineer or a flight test professional, what kind of data do you need and how do you analyze the data and what do you expect. So we'll start with the roll mode. Roll rate is more dominant than yaw rate, so the motion's almost pure rolling. This is an important measure of roll performance. More important for fighter aircraft than say transport aircraft or training aircraft. It's going to be characterized by the small time constant to give us fast motion. It's going to be an exponential response or first order response, and it's always stable. So for the FAA, they really don't address the roll mode, but you will see it in future lectures in the military specifications, MIL-F 8785B or MIL Standard 1797A, either one. I did show the route plot on the S-plane again. We know that the roll mode's a first order, so it's on the real axis, and that shorter time constants, the pole moves left, longer time constants, the pole moves right. We already talked about how for a linear system, you can change the amplitude of the input. It doesn't change the time constant. It just changes the value of the steady state roll rate. Now in flight test, we actually sometimes this is the step input coming in, and then the step input is taken out or controls go back to neutral. And in flight test, we often grab this data at the release point because it's easier to get this curve in flight than it is to get this curve in flight. And in the end, I can get the roll mode time constant either way. It's going to be 63% of this curve or 37% of this curve. So just an interesting fact of practicality when you're looking for data in flight test. Here's a time history, whether it's a simulator or an aircraft. So the pilot would put in the step input here, so that's the aileron going in and the step input. You can kind of see as the aileron goes in, our roll angle starts to build, but eventually gets to a constant slope, which was going to show up as a steady state roll rate up here. So a constant slope on the roll angle plot is going to show up as a horizontal steady state on the roll rate plot. You'll see here how we do this in flight test with NASA. So for a fighter aircraft, you do have to do a full 360-degree roll. And you probably heard the pilots say paddle on, paddle off. And what happens, and I've done this in the F-16 in the back seat. The back seat is kind of the safety pilot or instructor pilot seat. And on the actual control stick is a paddle switch, so that if you don't like the way the front seat person is flying, you'll push the paddle switch and override all inputs from the back. So what we do in flight test, and it's the rare time I get to actually touch the controls, is I will turn the paddle switch on, which means I'm overriding the pilot's input. Then we'll have the pilot put full or 3/4 roll stick in, hold that so that it's nice and steady, and then when I release the paddle, it gives me a nice abrupt step input. So you heard paddle on, and then the input came in, and then at the end of the 360, you'll release the paddle off, and that gives us a clean reverse step back to neutral. Next, we'll look at the spiral mode in detail. It involves aperiodic changes in heading and direction of travel. It involves changes in the side slip, the bank angle, and our yaw rate after initial bank angle disturbance. It's characterized by a time constant if it's stable. If it's unstable, it's going to be a time to double. So it's an exponential response, whether it's stable or unstable, relatively slow, And we can see in many aircraft it is unstable, and it is responsible for many accidents, at least in the early days of aviation, because if pilots got into clouds and got into a spiral, they called it a graveyard spiral, and weren't aware of it because of the slow motion, it's kind of insidious, they eventually would find themselves at a really high bank angle and not able to recover. So when we look at the spiral mode, we'll be on an initial flight path, and then we'll get a disturbance here in side slip, and then it really depends on what's going on with the aircraft. If you have directional stability that's too large, so C and beta is really stable, but we have inadequate lateral stability, then we can end up in this kind of spiral divergence where our airplane bank angle is going to increase slowly, causes the side slip to increase, the airplane flies in a tighter and tighter spiral. The other option is we don't have enough directional stability, so C and beta is not big enough, and then so we'll get this type of a profile, and we'll be directional divergence. So again, the FAA doesn't always address the roll or the spiral mode, but we'll see it in military specifications. We'll go over military specs in a future lecture, but I'll just give you a taste of what it looks like here. At least in case of the spiral mode, it says that the time it takes for the bank angle to double after a small disturbance should be at least 20 seconds. So we really want that time to double to be as large as possible, and 20 seconds is the smallest value. The way you test this in flight is you're going to get to a small disturbance in bank angle, so 5 degrees of bank angle. You'll release all the controls, and then you'll just basically let the airplane respond hands off. So then you'll record the bank angle phi versus the time. And then when we look at the data, we just look at the plot and make sure we understand what the bank angle is 20 seconds after the controls release, and as long as it hasn't doubled, we'll pass. So here's some time history data that shows what this looks like. Here's our initial disturbance in the bank angle. So we'll put in some aileron, get the bank angle to go up to say 5 degrees, and then let go. So there's the aileron input, get the initial bank angle up, and then let go. So from here on out, this is free response. So everything's controls are neutral, and then we look at the bank angle over time. And in this case, the bank angle is coming down with time. So it's a convergent spiral mode. But you could also have the bank angle start to grow with time, and as long as it doesn't double in 20 seconds, you'll pass the spec. So now we'll look at the second order Dutch roll mode. It's oscillatory, so it's going to have a frequency and a damping ratio. It's coupling with side slip, rolling, and yawing motion, and it's really kicked off with a disturbance in side slip. Depending on the aircraft, it could be lightly or heavily damped, but we will get a frequency and damping ratio from that. The FAA actually does put a specification on the Dutch roll mode. You can see here in this paragraph, the Dutch roll mode is called out, and really all they say is it's got to be damped within 1/10 the amplitude in 7 cycles. In case you ever wondered where the term Dutch roll came, it was named for the characteristic side-to-side motion of ice skaters on the wintry frozen ponds of the Netherlands. So when people looked at the time histories, they saw this swaying back and forth, and then that's how it became called the Dutch roll mode. So we'll look at, obviously we said it's a second order system on the S-plane, so you'll see a pair of complex poles. And the way we're going to initiate the Dutch roll mode is typically with a rudder doublet. So we'll get some side slip going, but it's going to be a doublet. So rudder goes one direction, and then a second later goes the same magnitude in the opposite direction, and then back to 0, and then again it's released. So this is all the free response. As soon as the rudder input goes away, we look at the free response, and we see the oscillations, and then whether it's growing or attenuating. So if it has the damping ratio, and we can also get the frequency information off the time history. All right, here's another Dutch roll from simulator data. And again, sometimes the input to the rudder looks like a nice square step wave. Other times it can be a ramp, but it is typically abrupt like this and symmetrical. And then again, we're looking at the free response from this point on. You can also excite the Dutch roll with an aileron doublet, but typically the rudder is what's used. And so you'll see yaw rate, roll angle, and side slip. You can get different information off of yaw rate, but really the main time history we're interested in is the trace of side slip versus time. And we'll determine the damping ratio and natural frequency off of those. So just like the case for the longitudinal equations and longitudinal modes, simpler models can be developed for the lateral directional modes. And this is going to give us insight into the effects of our stability derivatives on a particular mode. It's going to be useful for our control design work, and really we can just start focusing mode by mode. The roll mode, primarily rolling motion, other responses very small. Our spiral mode, primarily bank turn motions. And our Dutch roll mode is primarily side slipping and yawing motion. So for the roll mode approximation, we can get down to a 1 degree of freedom, pure rolling motion. We talked about that before. So we're going to assume that the aileron is the only effective control input. We're going to ignore the rudder. We get down to that nice first order differential equation, and then just have a perfect equation for the roll mode time constant. It's just -1 over LP. And so now we know roll damping, whether it's LP or CLP, determines the time constant for the roll mode. So let's see how good this approximation works. We'll grab the Boeing 747 again. Given our LP of -0.4356, we see that the roll mode time constant for this approximation is this, but from the full model we see that it doesn't quite match. It does have a smaller roll mode time constant, so it gets pretty well at the initial response, but then the accuracy starts to decay after that. So still useful for control design purposes, but not the best model. You can see the discrepancies here, and here the two curves start to break away. But our initial stuff here is good. Initial analysis here is good as well. For the spiral mode, we can make an approximation by neglecting rolling motion and side slip rate, and the roll equation is typically neglected at this point. What we can get to are two equations. So down here I have an equation where I can solve for beta, so there's beta, I can solve for it, and then substitute it into this equation and get down to an equation where I only have two inputs now, or two things I need to worry about. This is actually the forcing function, but sorry, this would go on the other side of the equation. So I would have a nice homogeneous equation here, and then here's my forcing function over here. So that's the spiral approximation. Again, we get a nice characteristic equation, a simple first order type of characteristic equation. Then we can get the spiral time constant, tau sub s, based off of our information here. And so we know that the spiral mode is going to be stable for this condition. We know that L beta or CL beta, our lateral static stability criteria, means that has to be negative. So we can deduce that for the spiral mode to be stable, we need the product of CL beta CNR to be bigger than the product of CLR CN beta. So increasing the dihedral effect CL beta or the yaw damping CNR makes the spiral mode more stable. So we'll look at another example using the Boeing 747. From our simplified analysis, we got our spiral time constant to be 33 seconds, which is really way off from the actual full model. And so in this case, our approximation for the spiral mode is pretty bad and probably needs to be avoided. Next, we'll look at the Dutch roll mode approximation. So we can assume the motion entirely consists of side slip and yaw, so the roll equation again is going to be neglected. It'll get our state space equation down to a nice 2x2 for the A and B matrix, and so that's easy to do determinants and solve. So simplified model. Here's our characteristic equation, and again now we have a nice easy determinant to solve 2x2 as opposed to a 4x4. Gives us a quadratic. Once we have a quadratic, well then it's easy to determine using the quadratic formula what the natural frequency or damp frequency is, in this case the Dutch roll frequency, and then what the damping ratio of the Dutch roll mode is in terms of the various design parameters and stability derivatives. Back to our Boeing 747 for a sample to see how close this is. If I grab the A matrix and B matrix data for the 747, so here's the data for that model, it gives us a nice second order characteristic equation which is easily solvable using the quadratic formula. Results in a frequency, a Dutch roll damp frequency of 0.922 radians per second and a damping ratio of 0.109. So from the full model, not too bad. So similar frequency, and the real model has a slightly lower damping ratio, but not bad. So it worked fairly well for the Dutch roll. Maybe not the damping ratio so much, but pretty close and acceptable enough to use for a control system design. Let's look at the classical engineering trade-off of lateral stability versus Dutch roll stability. So we know that dihedral effect CL beta is driving the lateral static stability, and we need that to be negative. But if the magnitude of CL beta becomes too big, the Dutch roll root moves into the right half plane. So that means the Dutch roll mode becomes unstable. The spiral mode, however, is becoming more stable. So now we have a trade-off between lateral static stability and dynamic Dutch roll stability. And then when I look at the trade-off between directional stability versus spiral mode, we know that CN beta is driving the directional static stability, and for static stability CN beta is positive. So increasing CN beta makes the spiral mode less stable and increases the frequency of the Dutch roll. So now we have a trade-off between static directional stability and dynamic spiral mode stability. And here we are at the end of this presentation. In summary, we know there's 5 classical modes of motion to aircraft. The longitudinal modes are the short period and the phugoid. In this module, we walk through the roll mode, the first order mode, the spiral, which is a first order mode, and then the Dutch roll, which is the second order mode. And again, it's often easy to look at the fourth order equation that gives you those modes, as well as look at where the eigenvalues or the roots end up on the S-plane to know that the spiral mode, again, is first order, so it's on the real axis close to the origin, could be divergent or convergent depending on what side of the plane it is, and then the roll mode is far off to the left plane real quick, and the Dutch roll is a second order pair. That concludes the presentation on lateral directional dynamic analysis.